Hello everyone. Here, we present an application of hierarchical Bayesian regression in modeling multi-site neuroimaging data. We will show how the HBR can be effectively used to derive a normative model of cortical thickness across the human lifespan, and how such a model can be employed to shed the light on biological signatures of different brain disorders. These days the neuroimaging studies, especially in the clinical neuroimaging domain, are scaled up from small group studies in labs to national-wide large population research projects. Nowadays, the neuroimaging groups across the world join together to form big international data collection consortiums. Therefore, clinical neuroimaging has recently witnessed explosive growth in data availability, thanks to the recent advances in data sharing standards and protocols. Furthermore, recent advances in high-performance computing technologies such as grid computing, cloud computing, and GPU technologies provide us just enough computational power to process these big neuroimaging data. And finally, add to these, the enormous progress in artificial intelligence and machine learning techniques in the last decade. Such momentum has brought ubiquitous applications of AI and ML to different domains of science with a direct or indirect impact on human daily life matters. The vast neuroimaging data availability, extensive computational resources, and recent advances in intelligent data analysis, altogether present us with a big opportunity on the horizon. That is to bring the precision medicine to diagnosis and prognosis of brain and mental disorders. The ultimate goal is to enrich the classical symptom-based diagnostic procedures by incorporating the biological and environmental factors into the diagnosis and treatment of mental disorders. This hopefully can result in effective biological tests and individualized treatments to improve the quality of life of patients. However, every big opportunity comes with a big challenge. A big neuroimaging cohort generally comprises smaller neuroimaging datasets, each of which is independently collected at different imaging centers and via different scanning devices. Even data collected by similar scanners from the same manufacturer can hugely vary due to small variations in scanning parameters and configurations. Furthermore, these data are generally processed using different pipelines and toolboxes, each of which leaves its signature on the final derived statistics. Such diversity in data acquisition and data processing results in an unwanted variation in data, we refer to as the side effect. Due to the side effect, for instance, the recorded brain images and derived statistics of the exact same person with the same clinical situation can vary significantly from one center to another. Data harmonization is a common solution for handling the side effects in multi-site neuroimaging datasets. The basic idea in data harmonization is to regress out the side effects from the data. Combat is a popular data harmonization method in the neuroimaging community. Combat removes additive and multiplicative side effects while preserving the signal of interest in data. The signal of interest comprises the known sources of variations in data, which is defined as a linear or nonlinear function of covariates in the design matrix X. Examples of such covariates are age, gender, and cognitive measures. However, the combat, and in general data harmonization, has some problematic shortcomings. In the following, we will try to illustrate the two major problems in data harmonization via schematic demonstration. The signal variance in neuroimaging recordings consists of three main components. 1. The known variance that we a priori are aware of, thus, we can account for them when harmonizing data. Examples are age and gender. 2. The unknown variance in data that might have some clinical relevance but we have no prior information about. An example is subtypes and psychiatric disorders. And the last component is the variance related to batch effects in data, such as side effects that we are interested to remove them from data. It is very important to emphasize that these three sources of variation often correlate with each other. For example, it is very common that the participants from a certain dataset have a specific age range. In this case, the side effect correlates with age. These shared variances are depicted as overlaps between the circles in this demonstration. Combat involves three steps. The goal is to remove the batch effects while preserving the known and unknown sources of variance in data. To do so, first, combat removes the known sources of variance from the data. Then, it removes batch effects, and in the end, it returns the variance of the known sources to the residuals. As you can see, combat is unable to remove part of batch effects that is shared with known variance in data. In addition, it incorrectly removes part of unknown sources of variations in data with potential clinical relevance. The second problem with combat arises when we want to reapply our analysis to data coming from a new site. In this scenario, we need to recompute the combat parameters, and to do so, we need to have access to all data from all sites again. This can be a restrictive practical problem when we want to reuse or extend a model with small collected local data. There is a set of solutions to handle side effects when modeling multi-site neuroimaging data. This set of solutions can be seen as a spectrum, where at the one end of the spectrum we have the complete pooling solution. In the complete pooling scenario, we pool all data from all sites and learn the same set of parameters and hyperparameters to estimate the mean and variance of the signal. The complete pooling does not deal with side effects per se, but data harmonization can be used in advance to remove batch effects from the data. At the other end of the spectrum stands the no-pooling approach, where we independently learn different sets of parameters and hyperparameters for data from each site. The no-pooling approach addresses the side effects at the modeling level. However, it does not benefit from the richness of large data. Therefore, its parameters can be unstable for sites with a small sample size. In this study, we propose hierarchical Bayesian regression, or HBR, for modeling the multi-site neuroimaging data. The HBR lies in the middle of the spectrum, thus, it brings the bests of two worlds together. In the HBR, similar to no pooling, we allow the model to learn different sets of parameters for data coming from different sites. At the same time, similar to complete pooling, we learn a fixed set of hyperparameters. Here, the hyperparameters play the role of a joint prior over the parameters. They perform as a regularizer and prevent the model from overfitting on small batches. The second appealing advantage of HBR is the transferability of its hyperparameters. Assume we have learned an HBR model on a primary set of sites. Now, we want to extend the existing model to data coming from new sites, but we do not have access to the primary datasets. In this setting, we can use the posterior distributions of hyperparameters as informative hyperpriors for the secondary model. Such informative hyperpriors enable us to incorporate pre-existing evidence when re-inferring the model on new data. Then, the parameters of the new model can be inferred from data from new sites. This feature completes the life cycle of the model as it provides the possibility of model recalibration, without the need to having access to the primary set of data. In this study, we have benchmarked the HBR against Combat and other alternatives in a multi-site normative modeling scenario. In normative modeling, the aim is to derive a norm for structural or functional brain measurements on a large healthy neuroimaging cohort. The first step in normative modeling is to estimate a model from a set of covariates in X to a brain imaging unit in Y. For example, in this study, we used age as a covariate to regress the cortical thickness across different brain areas. The next step is to validate the model on a test set. If the model is valid, then its estimated mean and variance form a normative model of brain structure or function. Now when we observe the data from a new subject, its large deviation from the norm of the population can be interpreted as an abnormality in the brain, therefore, can be further analyzed in relation to different brain disorders. In our experiments, we used a large sample of 7,499 subjects from 6 datasets. Our experimental data cover almost the whole range of human lifespan from 3 to 97 years old. These data consist of structural MRI data from 33 scanners. As can be seen in the scatter plot, the side effect is clearly present in the data. We use the gender and scanner as batch effects in our HBR model. We compared the regression performance of HBR against no pooling, and complete pooling with, and without data harmonization. The predictions by the HBR showed a higher correlation, and lower standardized mean squared error and mean standardized log loss. Furthermore, when predicting data from new sites, the HBR showed a better performance compared to complete pooling and only model priors. In an anomaly detection setting, we further computed the abnormal probability index for each individual across 148 cortical regions, and used the area under the ROC curve to evaluate the predictive power of deviations for each clinical diagnosis. The resulting spatial distribution of discriminative regions largely overlaps with brain areas that are known to be implicated in the corresponding disorders. Nowadays, more than ever, we have access to large and publicly available neuroimaging data, and there is more to come in the next few years. Thus, the time is just ripe to benefit from these vast sources of brain imaging data, and try to find the right treatment, at the right time, for the right patients. To achieve this, we need international efforts to collect and share data. Yet, dealing with side effects remains a notable obstacle when merging datasets. Here, we showed the potentials of hierarchical Bayesian regression in modeling the batch effects in neuroimaging data. Our contribution opens the door toward implementing more effective exploratory data analysis pipelines in more realistic scenarios. An implementation of HBR for normative modeling is publicly accessible in the PCN Toolkit GitHub repository. We look forward to receiving your feedback. Thank you all for your attention.